So let's continue learning about 3D. So now I want to talk a little bit about how the projection works. So projection in 3D. Now, let's start by looking at slide 8. Okay. So projection is the idea of what do we do with this Z coordinate, right? So previously, with orthographic, we just squish it. Z doesn't make a difference. It's just there, and we just squish things in. But let's look at this picture here, and this is a classic painting, and you can see lots of weird things going on. One is, hey, look at that. The ceiling, this is an angle, that's the opposite angle. It kind of converges in like this. So we would say this has a bit of a perspective to it, and I'll come back to that very shortly. The whole room, the walls come in, it has that real room feel. But the people, they don't have that feel. The people in the back they don't look smaller, they don't converge. The people look flat. So this is, what's missing here is that these people don't have any of this perspective or the projection. This image looks a little funny because different components have different projections. And for a long time, the art world has been playing with, hey, what do we do with these projections? Can we mix? Can we match them? How do we create them? What do we do with the Z coordinate? What do we do with things that get further away? So this is what I'm going to deal with here. So as a reminder, we've already dealt with orthographic a lot. And the idea with orthographic is we just collapse the depth, right? Straight onto the raster. Okay, and we've done this in 2D, but it works, well, we've done it in kind of 3D, but it works in full 3D the same way. If we move our camera around, I'm moving my camera around some scene, my origin's over there, and the camera's looking, here's my raster looking at my scene, I can see a triangle, there's a triangle over here, there's a square back there, whatever. All that we do is we take this depth direction, this is my depth, and we just collapse it in. And so Ortho just does that, collapses the depth, no matter what orientation or location the camera is in 3D. So nothing changes with Ortho. Now it can get a little tricky if you start thinking about, wait a second, if my camera's looking in a funny direction, how do I collapse that depth? So Ortho collapses the depth no matter what direction we look in. So to answer my question about, well, I'm looking this way, suddenly how do I collapse the depth this way? Luckily, we've already solved that. We just use the camera space. We just do it in camera space. So it's actually already solved for us for free. You don't have to think about it. In camera space, I already have my Z going into the scene. I just ignore my Z, I collapse it in. Okay, perfect. So it's already solved in 3D. Nothing changes as long as we're using our camera transform. If we do it in 3D though, we also need to convert the Z. Need to convert the Z dimension to our normalized device coordinates, right? That's our -1 to 1. And so when you do Ortho in 3D, the command does go left, right, bottom, top, as you're familiar with. And then we have now near, far. Now, of course, these are our Z coordinate. The near plane is close to the camera, and the far is far away. Now I'm going to come back far from camera. Come back to this because it might seem kind of strange. Like, I'm looking in 3D. Why do I need to have a far and a near? Why can't I just look forever? Well, computers have limits. But I'm going to come back to that. So this defines, basically one way to look at it is, okay, I'm going to tell the computer my expected range for Z. Defines the expected range of depth. And this becomes actually very important, and we'll learn lecture after lecture more pieces of why that's important. Okay? Yeah, my little star there. You know, more soon. So basically, Ortho in full 3D, it works just the same as in 2D. We move the camera where we want in 3D space, just like in 2D, and it'll just collapse the depth for us. It's no big deal. So Ortho is easy. Now, when we get to 3D, one of the things that really defines what people think about when they hear 3D is what we call the perspective projection. Often when people think 3D scenes, they think this perspective projection. So it comes down to the fact that we don't see the world in an orthographic sense. So we do not see the world orthographically. If I look out on a mountain scene, I don't see the Z collapsed. I see in like an angle. I see things that are further away. The further away they are, the smaller they look. There's so many properties. We don't see the world flat. Okay, we see it with depth. So the first thing I want to note is that our field of vision is actually a cone. Is a wedge triangle. Okay, so if I draw my eye over here, we actually see like this out into infinity. Okay, so if I want to draw a couple things in here, here's a person, you know, there's another person right behind here, another person back here. I'm going to draw some trees. Okay, my big trees, nice trees. So we have a scene here. So the first thing I'll note is we see wider further away. That's kind of cool if you think about it. Here, this might be, you know, 3 meters. This might be 300 meters across. And the further away, you'll see for kilometers, right? And as a side effect of this, because we see wider further away, further things look smaller. Okay? Now the other thing that happens is our viewpoint, because of this thing happens, we get parallax. So our viewpoint changes the impact of the depth. It changes the scene. We get parallax. Now, I'm going to highlight that. If I move sideways, if this was orthographic, anything I can still see would still be flat. It would just shift with me. But here, for example, I might no longer see this person. They might be blocked by this other person. The tree moves, you know, the tree might move a lot, or this person might move just a little. Or the tree might move a little, rather, because it's so far away. So we get this parallax. And also, as a result of all of this, as things move further away, they appear to approach the center of my vision, a vanishing point. They go off into the sunset, really. They approach a vanishing point. Okay, so if I'm going to draw my vanishing point here, okay, my axis rather, and if this is my vanishing point, if this person runs away, they won't stay the same spot. They'll seem to be approaching this line. And because of this, then parallel lines converge. So perspective projection is really strange. there's a lot of really weird things going on here that we might not have been thinking about before, that we certainly didn't have to think about with orthographic. So perspective was worked on a lot by the art community. People would take string and tie it to a wall and say, here's where I'm looking from, here's my view plane, excuse me, and then here's a point in the object, and they would map how things changed. A lot of the work on perspective projection was done in the art world, and the mathematics were developed there. Here's an example of some of the things I talked about. Where am I? Here we go. So I have these three objects, but because I have this vanishing point, because they're 3D objects, the things that are further away, they approach the vanishing point. So even if these three cubes are identical, I can see the front of all three, but I can see the right side of this one and the left side of that one because they're approaching my vanishing point. You get that feel. I can see the bottom of this one, but since this isn't the center, I can't see the bottom or the top. I can see the top of this one. So basically, wherever they are in the scene, of course, I get a line of sight differently as they approach the vanishing point. Okay. And here's a classic one. I used this in 1010 when I taught it. The railroad. These are parallel lines, but they appear to converge toward the vanishing point as they go off into infinity. Where am I? Okay. That was slides 9 to 11. Oh yeah, I want to do a demo too. Slides 9 to 11. I'm going to demo sketch 1. Where is it? Let's go back to my desktop. Cool. So here's an example of playing with perspective versus ortho. So this is actually an orthographic projection. I'm going to zoom in for you. And you might think, oh, just a cube is not a big deal, and you might not really notice that orthographic is a problem. But you'll notice this line is the same length as that line. It's hard to tell which is in front, which is behind because it's orthographic. You don't have the depth cue, and it doesn't quite look right. Oops. And if I rotate it, animate, there we go. If I animate, now it starts to look strange. This is orthographic, and they line right up perfectly and disappears, and it feels kind of wonky. Let's reset it to a nice, there we go. So here's orthographic, here's perspective. Now at first it's a bit jarring, whoa, it looks wonky, but the more you look at it, the more this is naturally what a cube would look like. I'm looking inside the box, and if I rotate it, hey, now that looks a lot better. So in this perspective projection, things that are further away, they approach the center, and so you get that natural feel. If I change back to orthographic, it looks kind of unrealistic. Oops, what I was trying to do. This one here, right? When I center, the back is further away, so it's smaller. If I change it to orthographic, they line up because I'm collapsing that Z direction. Cool. Okay. So I want to talk a little bit more about the differences between perspectives. So projections, rather. So projection comparisons. So perspective is pretty cool. It's the most realistic one for sure for humans. But it actually has a lot of problems. If you've ever done any architecture or cartography, you've probably thought about projections before, but there are actually some problems with perspective. Okay, and it's the fact of having size depend on the distance makes it hard to read. I should do it this way. But yeah, we got it. Having the size depend on the distance, it causes problems for us. And it surrounds the fact that this is no longer, it's not an affine transformation anymore. Okay, this is not an affine transformation. Parallel lines don't stay parallel, right? Proportions break. Things that are further away, the proportions break. Okay, so it's not affine. So parallel lines, ratios, right? They all break. Now, think about engineering for a second, or architecture. If you have a rendering of a scene, you might want to depend on ratios. You might not want to be able to grab a ruler and measure something. You can't do that, okay, with perspective projections. You can't do it. So we have some other options. Orthographic still, to this day, is where am I? Very popular. Come on. My computer froze, of course. I'm going to not sure why this OneNote is so terribly behaved. Okay, so orthographic, of course, is nice because you don't have those problems in orthographic. And I'll show you a slide in a second, but it maintains things very nicely, so you can use it for engineering, you can use it for architecture and for design. But we also have a few others I want to briefly talk about. We won't go into these deeply, but you need to know about them. There's isometric, and isometric is basically it's an off-axis angle. So it's like orthographic, but you know that's an orthographic cube, right? Because you're looking straight on. Whereas isometric might be something like this. So it's off-axis, so I can look at it, but that maintains ratios. So it looks kind of 3D, and we can see the depth and the angles, but we maintain the ratios, we maintain the parallel lines. So that's isometric. And there's also, and these are basically done, we do these by moving the camera to have point where we want, then do ortho. So these are actually pretty easy to do. We move the camera exactly where we want, we do ortho, bam, we maintain everything. Another approach is oblique projections. And they work a little differently. Instead of just doing ortho from a different perspective, what they do is they add a shear along the z-axis. So literally, I'm in the z-axis, it moves things sideways, like not like turning it, but it moves things sideways. It shears the whole z-axis, so I can see the front perfectly without any perspective, without any shift, but I pull things sideways so I can see the side face of it as well. Those are called oblique projections. And in both of these, people can rely on measuring if it's done properly. Of course, with oblique, it depends how much you do this, and you need to know your ratios. But these are standard, they're fixed, they're much easier to learn and to standardize than the perspective where things change with depth. So I'm going to show a couple more slides on this. Where's my window? Come on, PowerPoint, you can do it. So this is what I was saying about orthographic. So we have an orthographic here, and even if this is deeper, it doesn't shrink. I can rely on the ratios from this perspective. If you're building something or engineering something, this is very important. You need to know the size of these things, grab a ruler and measure them exactly. You can't worry about depth changing it. And this is an isometric view. It's still orthographic, but we have this turned view. Okay. Here's some axonometric projections. These are standardized isometric ones, and they have standard angles and standard ratios, so people in different fields, will work with them and be familiar with them. Purely isometric, you have the offset x, y, and z to be the exact same angle here. So it's a perfect, it's a balance between the three, but you can reshift this, and there are different standards, but we're not going to get into it. Here's what oblique looks like that I mentioned. These, again, they don't really, the parallel lines will stay parallel, but it will break the proportions. Cavalier is the most exaggerated one, but it just stretches the thing sideways. And again, you have standardized ones. Cabinet 60, cabinet 45. Notice here, A, this is half A, right? So people learn these ratios and how to use them, and it's very common within certain fields, okay? And then, just another slide comparing that. You can look at this in your own time. This has been very popular in games, some of these isometric views. They're not really 3D. It was useful before we had real 3D engines to set artwork in a standardized viewport. And so you can get this 3D or this view of being above or seeing depth without having all the complexities of real perspective and real 3D. You know, we have these games here. On the right is perhaps one of the best games of all time. Certainly has a cult following. So that's that. So I'm going to go back to the... I want to do a sketch, actually. A demo. That's what I was going to do. So this is an example of a... Come on. Did I hit the key? This is an example of Oblique, what Oblique looks like. So we have this thing 3D, standard 3D rotating, but this is what I want you to look at here is this Oblique thing, and I can actually change the Z shear. Of course it moves, I could fix that with my translation, I'm just too lazy. But you can shear the Z, and you see that the proportions don't change. Of the parallel lines don't change. And I can go all the way to Cavalier if I want to. That's what Oblique looks like. Cool. Alright, so that finishes it for this section. We're going to come back and learn about view volumes.